Good afternoon. Thank you for connecting back to our classical machine learning workshop. So this is the wiki page for our workshops. And so we go inside classical machine learning. And we're going to see today ensemble methods. So we select that wiki page. And so what is exactly ensemble methods? So ensemble methods, it will be just handling a combination of different algorithms to get your results. And so there's not any specific algorithm that does the processes. You will find several links over there on what are the basic definitions. And we continue using SciKit Learn library from Python. And so the first method we will talk about is going to be bagging, and which is a short term for bootstrap aggregating. And bootstrap is when you have a set of items and you start extracting items from the data from the set, but you are replacing every time you extract one. Okay, and this method is the goal for this method is to reduce the variance of the methods of the models, and we will be using several base algorithms to construct a bagging process. So the basic processes algorithms, base model algorithms are decision trees. Decision trees are just binary trees. It's just go and splits into different branches, and you continue splitting and branching out until you get a number of levels. You can control the number of branches at any node, and also you can control the depth of your tree. Another one is just the nearest neighbors algorithm that can cluster different items defined by their properties. And also we have support vector machines, which is also a separation of your items of some data set in your space by different regions. Okay. So when you're using, for example, this algorithm bagging classifier, remember we are going to be working with two types of tasks. One to be a classifier, and the other one can be a regressor. So classifier just classify your items, and regressor is just doing an estimate of a numerical value depending on your original data set. Like when you do the least squares method, that's just regression, linear regression, for example. So those are the two types of tasks we can do with our data sets. Okay, so this is the very brief code how to use the bagging classifier, and then we will use the model logistic regression. And then we define the base model will be the logistic regression, and then that base model will be input into the bagging classifier, and we will say how many logistic regression algorithms we want to try. So we start with a collection of 10 logistic regression algorithms, and the bagging classifier will just play with this model, and then once we have this model, the bagging model, then we are going to give the X train and Y train, and we are going to fit the model to this initial data set. Your X train is when you have a data set, remember we split into training and testing, and the training, usually we take about 80% of our data to train our models, and then 20% left to do the testing. And then once we have trained our model using the fit function, then we can just try to predict what results can give into using the test data. And then we will compare the predicted values with what we already know that's true, the test, the white test, and then that will give you some accuracy of your method. Okay. We will go into an example later. I'm just going to present the 3 different methods. The other method is boosting, and it's used to reduce your bias of your models. And you can train these sequentially using different base models. And every time you have some results, then you start learning from your misclassified data, and then you just try to give more weight to the part where you have the different data in order to reduce your bias. You can also assign different weights to the misclassified points for training your next model, and then you combine the predictions using some weighted sum or some weighted both for the classification. These are the common base models used in boosting. We have also, again, decision trees, and then from those decision trees, we can use AdaBoost and gradient boosting. We can also use linear regression, and inside linear regression, we have several options like the lasso regression and the elastic net. The difference between the two is just how you handle your metric for measuring the errors. Here you're just using the absolute value of the difference, and here you're using the absolute value squared of the difference. And also you can use support vector machines. And this is an example how to use the AdaBoost classifier. Again, you define your basic model, you import AdaBoost classifier, you define your base model as a logistic regression, for example, and then you construct your AdaBoost classifier with your base model and the number of estimates. So you have 10 logistic regression algorithms. Then your boosting model are fitted to your training data, X, Y, and X train and Y train. And then the X train, for example, we're going to be using at the beginning the example of the penguins data set. So the X train data or the X data set is just going to have all the different measurements from the penguins, and the small Y will be just the species, for example. So we will try to classify our data set by species in the case of the penguins data set. Once you fit your model, then you try to make some predictions with the model. So you predict based on your testing variables, and then you compare your prediction with your actually target. The same thing you can do with the AdaBoost regressor for doing regression fit. And the third method is just stacking. The stacking method is just going to be used for improving accuracy. And you can use several types of algorithms. It doesn't have to be the same. And then at the end, for example, you will just take a voting process. So this is the example, for example, of the voting classifier. So we import the voting classifier, and we define several models. The first model will be a random forest classifier, and the second model can be an AdaBoost classifier. We are starting with 100 trees on each case. And then we construct an ensemble, and it's going to be a voting classifier using the different estimators, so the random forest and the AdaBoost. And then we say how are we going to consider the voting, if it's going to be hard, can be soft, or can be soft with different weights for different models. So you can give different weights to each model, or give different importance in the voting process. And then once you have your ensemble, you feed it with your training data. And then once you have trained your model, then you just start to predict based on your testing data set, and then you compare your predictions with your real values. Okay. And just in summary, what is the difference between the three methods? The learning style, for example, for the bagging can be in parallel. You can be working in parallel. The boosting has to be sequential because you are learning about your misclassified data, and stacking is just using different algorithms. So the base model diversity, in the case of boosting, you can use the same method, the same base model, and in the stacking, you use different algorithms. And these are the focus. The first one for bagging, reducing the variance; for the boosting, reducing the bias; and for stacking, improving the accuracy, and so on. Okay, so we have an example for a Jupyter notebook, as always. So we open this, and then once you open it, you can open it in Google Colab and save it to your Google Drive, and you will find something like this. Okay. Right. So let me know if you have any problems or questions. And we will try to, this Jupyter notebook is very long. I have several examples, so we are not going to cover everything. We are just going to follow up the general discussion, and the method will be almost the same for every algorithm. We have to have a data set, then we split our data set into training and testing, and we will use the different SciKit Learn functions. So we have to use the training test split to split our data set into training and testing. And then we import the decision tree classifier from the tree libraries. We will use different metrics depending on what we're trying to do. So if you're doing classification, we will talk about the confusion matrix and do a classification report and display the matrix and measure the accuracy score. And also, if you're doing classification using trees, there's a function for plotting a tree. And then we're doing regression, then we'll use the accuracy score from the metrics. Okay, so we run the first cell. Then, as we have been using the penguins data set, I'll do it again. So I read the penguins using the read CSV function, and and the penguins data set is sitting over a GitHub repo. This is how the penguins data set begins. Remember, we have species, we have islands, we have the different measurements, and we have the gender of the penguins. And also, then we can start doing some exploratory analysis. We know that we have some missing values, so because not all the columns have the same number of rows, and then we see that there's some missing rows for the different measurements. So we drop the rows with missing numbers, and now remember, we have seen in the past that the penguins data set has, this data set has 3 genders, male, female, and a dot. So we need to eliminate, or keep only the rows that have the gender or sex not being a dot. So I do this command. And then we can use Seaborn to visualize a scatter plot, how every variable depends on the other one. And also you can look for different correlations based on species. So we are going to be using this data set to predict the species based on gender and other physical measurements of the penguins. Okay, just a box plot of the different species by gender, and we have some outliers. Okay, and then now we will start doing the machine learning part. So which is called feature engineering. Feature engineering, you start to study what is the relevance of each variable or each column in this case. So we have several columns for the measurements. And we use the pandas get dummies function. And what it will do is leave the numerical variables as they are, but it's going to be working on the categorical variables. So the categorical variables in our case are the species. We have 3 types of species, Adelie, Shinstrap, and Gentoo. And we have the island. So the island is the Bisco, Dream, and Torgensen. And also we have the gender, female, male. Okay, so that's the get dummies function from pandas. And then there is another thing that we can do in order to reduce the dimensions. So for example, in the case of the binary variable, which is the gender, female, male, we can drop the first one and only keep the second one. So if a penguin is a male, we'll have a 1. But if it's a female, we will have 0 value for the male, right? So the first variable can be redundant, so we can just drop the first one and just keep the second one to denote the gender. And we do the same for the islands. So we don't need 3 variables describing the islands. We can always keep the first or the last 2, and if it's 0, 0, it will belong to an island of Bisco. And if it's a 0, 0, 1, will be Torgensen, etc. And the same thing for the species, but we're going to drop the species in the next one. We're going to drop the species, and we will try to create a model to classify the penguins data set by species, and using just the general other variables. So we're going to drop the species, the columns, and we're going to drop the first variable from the dummies function. So we do that, and what we get is we have the numerical variables. They're continuous to be the same, and now we only have 2 variables for the island and only 1 variable for the gender, and that's enough because if it's a 0 male, that means it's a female. Okay. Okay, and then now that we have this data set, which will be called X, capital X, and Y will be just the column for the species. Okay, so we will have this is the X data set, and this is the target. So the target is just the species of the penguins. So we will use the first part of the data of the penguins data set, now composed this way, to predict what species the penguins are. Okay, so we're going to use the train test split function to split your data set into X train, X test, Y train, and Y test. We're going to split 80% for the training and 20% for the testing. And this is just a random variable initialization. Remember, we don't have actually random variables. We have pseudo randoms. So we need to put some number here. It can be any number, just to have reproducibility. So every time you run it, you have the same results. Okay, so we do that. Now, for the training size, we have 266 rows, and for the testing size, 67. Okay. And now we're going to be doing a decision tree, and we're going to be first doing the decision tree classifier. Okay. So we define our model as the decision tree classifier. And we remember we loaded the decision tree classifier in the first cell. So we run it now, And then once we have our model, we feed the model with the training data, the X train and the Y train. The X train are just the measurements for the penguins data set, and the Y train is just telling what is the real species for that row. So we do that. Okay, so now we have our model fit to our specific data. Now we're going to predict for their model using the predict function for the testing. And then we were going to predict the training and do that. So now we have prediction based on the training data. And then we have to evaluate. Okay, so we're going to compute the confusion matrix and see how it went. So we are going to compare the prediction versus the testing value. So the prediction will be the species predicted by the algorithm, and the testing is just the actual values of the species. So actually we have, in this case, a very good classifier. The decision tree classifier can predict very well if a species is from, I don't know, the first species. So it classified very well the 31 penguins from the first species, 13 from the second species, and 23. And you will find there were no penguins rows misclassified. So in this case, we compare the prediction versus the testing. The testing is the real value. The prediction is just what came out from the algorithm, and we have an accuracy of 1. And the same thing, well, between the predicted train and the Y train also is going to be 1. So we have these are columns of the X data set. We are just penguins dimensions, the island, and the gender. And we can ask what are the feature importances of our model. That means the model, how is it looking for the different variables? And it give me this array. I can just do it explicitly. And this is the feature importance. So in classifying the penguins, this is the relevance of each column. And you will see that the body mass had no effect. The same as the Torgensen Island. And so we can drop the body mass. Let's see, before doing that, we are going to do the visualization of the tree. And in the decision tree algorithms, there's a Gini coefficient, also called the Gini impurity, and measures how often a randomly chosen element from a set will be incorrectly labeled. So if a Gini coefficient is 0, means that everything that is collected is correct. So we do the plot using the function plot tree. And this is the tree. So this is the first branch. So it's if the flipper length is less than 206.5, and there's a Gini coefficient of misidentifying or misclassifying. We have 266 data, which is the testing. And then it will split into 2 branches by the Kuhlmann length and the Kuhlmann depth. And then each branch will continue splitting into 2 until it gets a Gini of 0. So it goes here and then splits back again by Kuhlmann length less than 4655. We have a Gini of 0.4. Continue until we get Gini 0. And we do the same thing with the other parts until we get a Gini of 0 in all the end parts of the tree. So we have Gini 0 here, Gini 0 here, Gini 0 here, same here, and same here, and same here. So that's how the tree classifies your data by following this decision tree again until the Gini coefficient is 0. Okay, the next step is pruning. Pruning means I don't need some variables, so I'm going to drop the species and the body mass. You saw that the feature importance, what? Let's go again. Yeah, because I'm using DF. So DF is the original data frame, so I need to drop the species and the body mass from the columns. And I'm going to use the dummies function from the pandas library. So I'm going to drop the first dummy variable. So we saw that it's redundant. And then we will call the Y is just the species column from the data frame, original data frame. And then we use the test split function to split between the training and testing. We're going to be defining a 20% of the testing of your data set, and we define a random state for reproducibility. So we can do this again. Now, there are two methods to look for the optimal parameters or hyperparameters of your algorithms. One is just going and playing, like how many times can a node split and how many depth, or what is the depth, the number of levels a tree can achieve before finishing. There's another method which is called the alphas. So we're going to be using that. So we use the function cost complexity pruning path, and we apply it to the model, and that will create a path, and then we will extract the functions from the path, the alphas. And this gives me an array of values, some small values always. And then we can try to find the accuracy of our model. Okay, so we are still classifying using the Gini criteria, and we're going to use all the different alphas, and then we will try to see what gives me the best accuracy. Okay, so this is a loop for all the different alphas.
We have a question in the chat about the Gini coefficient. If you want to take a look at it.
Okay. Christopher, did you clean your penguins data frame? Remember that the original data frame had 3 values of gender? And also, if I change the testing training split into, let's say I'm gonna split it into 30% for testing and 70% for training, I will get different results. Okay, so I'm doing that now. I will have different alphas, and then I'll have different accuracies. Okay, and so this is the different alphas, and you see that the accuracy is improving as the alphas is decreasing. Okay. Well, okay, and you're using the same random state number to start. Okay, we can talk at the end. All right, so the next thing is just doing a pruning for the different alphas. This is another way of doing it. So we're using the cost complexity pruning path and computing the different alphas and impurities and plotting. And we will have this alpha. So the number of impurity leaps decreases as alpha goes to 0. And then we can compute the number of nodes in the last tree with alphas. So the number of nodes in the last tree is 1, with the alphas being 0.32. Okay, so this is just a different visualization. It needs a lot of interpretation for your algorithm, but it just tells you how well your algorithm is doing. And then you know that you need to, I'm going to skip this, you need to select some alpha to produce your plots. Okay, so that's classification. Now let's go and do a regression using decision tree. And we're going to change from a data set. No, now I'm going to be using the diabetes data set that comes inside the SciKit Learn. So SciKit Learn comes with a different set of toy data sets. So let me see if I can. Okay. Depends on what task you're trying to do. And so you have all these different data sets. You have the diabetes, you have the digits, you have the iris, you have the linear wine, and the breast cancer. And depending on what type of task you're trying to do, a classification or regression, so we're not going to be doing a regression. So we're going to be using the diabetes data set from SciKit Learn. And we go back. And we start again. We import the data sets. So we define the data frame as diabetes, or the data set diabetes. And then we're going to separate. Our target will be if the person has diabetes or not. I assume this will be the glucose level. So I just print a sample of 5 rows. Okay. And then the X diabetes data set will be all your different parameters for some patient, except for the target, if it has diabetes or not. So that will be the X, and the Y will be the target, meaning the glucose level. So I do that. So then I use the trains test split function to separate into 80% for the training and 20% for the testing. And then I will now use the decision tree but regressor and call it DTR. The model will be called DTR, and we're going to feed that model using the training data. So we run it, and then we measure the. Now, since we're doing a regression, our metrics will be like the mean square error, and we take the square root of that. So we predict based on the testing values. We predict for the testing values using the fitted model, and that we call it the Y prediction test diabetes, and then we compare that value with the original one, and this is the accuracy. And we compare the trained diabetes data versus the predicted trained diabetes data on the target value, and we have precision 0. I mean, yeah. The error being 0, mean square error. And then we compute the alphas, and then we compute the root mean square error for the different alphas and plot it. Again, the error, the root mean square error is increasing as alpha is increasing, but we have to select an alpha that is very close and has a close value between the testing and training. So I'm going to select an alpha in this vicinity, something between 0 and 250, let's say 100. So I'm going to put here 100. And then I'm going to define this model, the decision tree regressor, as DTR. with alpha 100, and then I'm going to fit my model using the training diabetes in X and Y. And now I have my model fitted to my training data, and then I can compute the root of the mean square error of the difference between the Y test diabetes versus the Y predicted from the model. And this is my mean square error, root square. I can do the same comparing the training versus the Y predicted training from the model. And this is the root mean square, okay? And this is the mean of the target or the glucose mean. And then I can print the decision tree regressor, how it came to the result we were seeing. But now we don't have Gini since it's not a classification. We have the square error as something that has to be minimized. And then we start with the BMI, the body mass index. This is the square error, the number of samples, the value for the target. And then it will start splitting until we get some error, a very low value of the error, okay? And we're not going to get zero error, never, okay? Then we can see what is the feature importance, and then we can print in columns, and we can see there's some, like there's no relevance from the age, the gender, I don't know what are these variables, but some variables are relevant to the model. Every model will see different degrees of importance of the different columns. So it will depend on the model. That's why we have to combine different models, because every model sees different relevance in your feature engineering. Okay, so that's the decision tree. Now let's go very fast and start looking at the ensemble learning. And the first one we're going to be using is the bagging classifier. So we're going to define a bagging classifier, bag CLF, and we're going to be using 20 estimators or 20 trees. And then we're going to fit our model, the bagging classifier, with using our training data, X and Y. In this case, the penguin's dimensions and the penguin species. We train our model. Now we have the training model, then we have to predict what is the value that the model predicts for the testing value, and the same for the training values. And then we print the accuracy, and then we see that the accuracy is very high. So that's a classifier. We can do now a bagging regressor. So we import the bagging regressor. We're going to use 20 estimators, and we call bagreg our model. And then our bagreg model will be fitted to our training data for the diabetes, since we're doing a regression. We do that, and then we compute the root square of the mean square error. We have 55. And we do the same thing between the prediction for the training and the predicted and the white train, the real white train diabetes, and we have this mean square error. Okay, we can continue doing this bagging classifier using a different algorithm. So we can use the Gaussian naive Bayes classifier. So bagging classifier, but the Bayes estimate now is a Gaussian naive Bayes, and that's called NB_CLF. That's the model. We feed that model using our training data. And now we can predict with our model the values of the testing set and the training set and compare the accuracy between both. So this is the accuracy score for classifying the penguins data set using that. Okay, so that's bagging. Now we can do voting classifiers. And voting classifiers, we will use different classifiers. So we are going to import the voting classifier. We're going to import the logistic regression, the Gaussian naive Bayes, and the random forest classifier. We're going to define 3 classifiers, one for the logistic regression, one for the random forest classifier, and one for the Gaussian naive Bayes. And we use these parameters for the logistic regression, solver LBFGS and random states. Random forest, we're going to have a forest 100 trees. And Gaussian naive Bayes, we'll leave it as it is. And then we will find 3 voting classifiers. The only difference is if the voting is hard, if the voting is soft, or if the voting is soft, but we give different weights. So let's execute. And then let's just look at the first one. The first classifier, we are fitting our first classifier using our training data. And then we predict what our voting classifier gives. And then we can print the accuracy, comparing what we have the original value compared to what the first ensemble classifier is predicting. And also we do the same for the white train and what the ensemble classifier is predicting on the training data. And we see a very high accuracy score. And then we can do for all 3 cases. Let's see. Okay. Yeah, so in this case, we are just going to print what is the result of each classifier using the ensemble classifier, the first one, which is the hard vote. And this is the logistic regression is giving a accuracy score of 1, the random forest of 0.99, and the Gaussian very low, 0.85. And when we combine the results from the first 3 classifiers and we take a vote, so the resulting vote from the hard, using the hard vote is going to be 1. That's the answer of the voting. If we use a soft vote and we do the same, but now using the soft vote, these are the results from the specific classifiers. Remember, they don't change. But now the vote is 0.98. This is doing a soft vote. And then we can do the same thing, but adding a soft vote and also adding some weight. So I'm going to add more weights on the second classifier. So the first one and the third one has a relevance of 1, a weight of 1, and the second classifier, which is the random forest, has a higher weight. So I do that. And I get these results. So the voting classifier is 0.98, right? Okay, another example for the random forest classifiers. Random forest trees are used very common because they give a very good result for classifying and also for doing regression. So we have this model, RANDF, random forest classifier, and we fit our random forest classifier to our training data. So now we have our model trained, and then we're going to predict the values of the X test and the X train and compare them. And then we print the accuracy, and we find the accuracy is high. And there is a out of the bag score, OOB score, for the random forest estimate, and without doing any tuning, this is the result from the random forest using the default values. This is the feature importance that the random forest sees, and this is how the random forest sees the relevance of each variable. So the culmen length has more importance compared to, for example, if they lived on the island Torgensen or they are male. Okay. The same with the random forest, but as a regressor. So we are going to use the diabetes data set. We feed our model, the random forest regressor, with the training diabetes data set. And then we can compute the square root of the mean square error. This is 55, comparing the result from the predictor compared with the real value. And we get something similar for the training data set. And the out of the bag score is just 43. Okay, boosting, we can use the ADA boost classifier. Let's go. So we define our ADA boost classifier as ADA underscore CLF. And we're going to use decision trees, the maximum depth of 1 and the number of trees 20. We're going to fit this model, the ADA classifier, with the training data. So we done that. And then we make predictions with the model. And then we compute the accuracy. And this is the accuracy of the comparing the predicting with the testing data and the training data. We can use the ADA boost classifier using the decision tree classifier. Now we can use the ADA boost classifier using a logistic regression using 20 algorithms. And this is, now we have trained our ADA with logistic regression using our training data, and then we can make the predictions using the predict function for the testing and the training, and then compare the metrics of the classification. And you can see they're almost one. Another boost using regression, we do it. So the algorithm is called ADA boost regressor, and we're going to use the default, and we're going to be using the diabetes data set, and then we make predictions once we have trained with the original data, and then we can compute the square root of the root mean square, and this is the error, the root mean square error. Okay, we can continue with the gradient boosting. So this is just a different scenarios using different algorithms in the three methods: the bagging, the boosting, and the voting or stacking. And then we're using two cases for classification or regression. So these are just examples. So the gradient boosting classifier, we will find that besides random forest trees, we have also the gradient boosted, and we will see another one is called XG boost classifiers. So these are very good algorithms, and you will get better results. So we can use the gradient boosting classifier, apply it to our X-train using 20 estimators, and then make the predictions and print the accuracy for classification. And this is the XG boost classifier. We load it. But now we're going to be using the WINES data set which is just a collection of wines of three, instead of species, three types of qualities. And we train our classifier, XGBoost classifier, using the wines data set. And we make predictions, and we compute the accuracy score. You will see a very high accuracy score. So this is the XGBoost classifier. We can play with different parameters for the XGB boost classifier. The learning rate is how it's learning every time. So you put a collection of large number of algorithms with a low learning rate, and then you will start learning from there. And eventually you get some good result. You predict, and then in the accuracy, you see that we have very good accuracy. So that's classification. The same thing can be applied to regression. So regressor, we train our regressor, XGBoost regressor on the diabetes data set. We make the predictions and then print the root mean square. This is the root mean square. Okay. Okay, you can continue tuning your algorithms, just playing with these values. Okay, so in lots of words, a summary of what is ensemble learning and what are the basic, let's see. That was here, classical machine learning. So this is the overview of the ensemble methods. And so it's not a single algorithm. You always are using a combination or an ensemble of different algorithms for doing classification or regression. And these are the three methods. And these are the common algorithms you can use. And this is how you use the algorithms. So you have a base model, you have the method classifier or regressor, and then you define your model, and then your base model, and then you train your model using your training data, and then you make predictions, and then you measure you do your metrics for classifying or regressing. So that's what I have today. Do you have any questions for me?